Hi, Algebra 2 Honor students. Today is going to be Unit 15, Day 2. We're extending our concepts of solving equations today to solving quadratic trig equations. So there's going to be some new notation that maybe we're not too familiar with yet, but we'll get very used to. And in each of the examples that we see today, I want to start mixing in not only solving in degrees, but what if we wanted solutions in radians? Now that we have a pretty good concept of what radians are, let's express some of our angles that are answers in radian form as well. And when necessary, we're going to round answers to the nearest tenth. So let's go ahead and get started with number 1 here. If you have cosine squared minus cosine x equals 0, I would have you consider comparing this to the equation a squared minus a equals 0. Right? If you use the dummy variable for cosine of x, if you let cosine of x equal a, well, then this term becomes a squared. And just for notation purposes, this is how we write the function cosine x squared. The squared goes kind of right in between cos and the variable x right there. So that might be a new looking notation for you, but something that we'll see actually quite frequently. This is cosine times cosine right there. All right, so if I gave you this equation, I said solve, I hope what you would all do to solve for a is think about the technique of GCF here. There's a GCF of a you would factor out. So very similarly over here, there's a GCF of cosine of x that you can factor out. And when you do that, think about dividing each of these by cos x. You get cos x left over from the first term minus 1. So the factoring technique that's needed to solve this quadratic would be GCF for the very first example. And because we're solving quadratics today, in as many cases as we can, we're going to look to see, do we have a factoring technique that will work? So then from there, you're going to set each of these equal to 0. Cosine x equals 0. And then over here, we get cosine x equals 1. And we want to figure out, well, what makes this true? What angles for x? And then what makes this true? So now we have it in terms of 2 linear equations, which is exactly what we did yesterday. I'm not sure we really analyzed this case, though. If cosine of x equals 0, does that ever happen? Well, yeah. I mean, think about the graph of cosine. Cosine definitely hits at 0 really in 2 locations, from 0 to 360. So if you look at the graph, you can get those answers pretty quickly here. Or if you kind of like the unit circle, we're looking at these 2 locations right here. And why those locations? That's where the x value is equal to 0, here and here. So you can either look at the graph or you can use the unit circle. Either way around it, you're going to get in degrees 90 degrees, and then 270 degrees. Okay. How about cosine x equals 1? Well, before I start thinking about triangles and specific quadrants, remember that this is a special case as well where you're going to use the graph, because cosine x equals 1 here and here. That's the max value in the range. So this is not an example where we draw some triangles. This is also unit circle, but it only occurs at this location right here. The x value is 1 at 0 degrees and also at 360. But remember that we usually don't accept both of those answers because it's kind of like repeating the same answer twice. So if I look back at the original interval, it says include 0 as an answer, but not 360. So I'm going to cross off 360 and say that we have 3 solutions to this equation for number 1. Let's list them in degrees first. So for part A, you would say that the answers are x equals 0, 90, and 270. And for part B, if we're going to list answers in radians, well, 0 in radians is still just 0. You don't even have to put a pi next to it unless you really want to. 90 is pi over 2. That's a quadrantal that I want you to be pretty familiar with. And then 270 is 3 pi over 2. So just getting used to listing answers in both formats. I really want you to think about both of those things. And you could do a quick conversion if needed, but hopefully these are ones you're pretty familiar with. All right, so that was a good example to get us started with solving trig equations. Let's move on to something along these lines. So if I gave you for number 2, 2 sine squared x plus sine x is equal to 1. Again, if you want to compare it to something that we've solved before, you can use a dummy variable here and say, this is the same thing as 2a squared plus a equals 1. if you let a equal sine x. Now, when you have a quadratic, it's super critical to set it to 0 before you decide what technique you're going to use. So don't look at this and think, oh, GCF, just like the last one. You can only use GCF here because it's already set equal to 0. But for this one, you're going to go ahead and subtract the 1 to the other side and then think about, is there a factoring technique for that? Well, let me jump back over to the one with signs in it and see if we can reason our way through with leaving with signs instead of using that dummy variable like we've chosen over here. Well, when I break down a quadratic where there's a lead coefficient, we just want to be a little bit cautious about the technique. Things that multiply to 2 sine squared are going to be 2 sine x and sine x over here. Yes, those definitely multiply to sine times sine is sine squared. And then 2 times 1 would give you the 2 out front. Well, the nice thing about the factoring here is that there's only one option of things that multiply to 1. It's 1 and 1. But we want to get a negative 1 here, so we do have to consider, where do the signs go? Is it plus 1 here and minus 1 here, or is it the opposite? Well, we're checking on trying to get positive sine x in the middle. So when you do this type of factoring, just make sure that wherever you choose the plus and minus, that they're in the correct locations to get a plus sign in the middle. And actually, to make that happen, it's going to have to be 2 sine x minus 1 and sine x plus 1. How do I check that in my head real quick? The outside is 2 sine x. The inside is negative 1 sine x. 2 minus 1 gives you positive 1 sine x for the middle. Perfect. Now I can go ahead and separate my factors. It's now like solving 2 linear equations. One is 2 sine x minus 1 equals 0. The other is that sine x plus 1 equals 0. So just like we did in yesterday's lesson, now get each of these to get sine x alone. I'm going to just jump right to saying that over here, sine x equals a half. And that over on this side, sine x is equal to negative 1. All right, so hopefully you can get sine x alone pretty quickly. Let's talk about the left side first here. For the left side, we've got all-star trig class going on. These are going to be some triangle pictures as opposed to what we've done so far with the graphs and unit circle. So sine x equals a half in the quadrants where sine is positive, which is quadrants 1 and 2. So that's where you're going to draw your triangles. Here they are. Sine is opposite over hypotenuse. So from your reference x, opposite over hypotenuse, we can label those. And this is looking pretty familiar to me. I've seen this triangle many, many, many times before. It turns out that we know the last side is radical 3. Okay, technically in quadrant 2, that's negative. But once I have all that labeled, now I want to get my 2 solutions. Well, one of the solutions is x equals, what's the reference across from the 1? 30 degrees. Okay. Now the quadrant 2 answer, if this is a reference of 30, would be 180 minus that 30, which is 150. The 2 solutions in degrees that we get from this side are 30 and 150. Okay, let's talk about sine x equals negative 1. This side, it seems like we should draw triangles in the quadrants where sine is negative, but I'm going to stop myself because I know it's actually a unit circle question. It gets, just with more practice, easier to recognize when we need the unit circle or the graph of sine x as compared to when we draw triangles. Okay, remember that the range for sine is negative 1 to 1. And if we're looking at values at those extremes, negative 1 or positive 1, you're going to use one of these 2 things, the graph or the unit circle. Okay, that's the point 0, negative 1 down here. Sine does correspond with the y value. So the solution there is 270 degrees, which you can confirm just as well by looking at the graph. Those are my answers to part A. We have 3 answers again, 30, 150, and 270. So I'm going to list those accordingly. So in part A, the solutions are 30, 150, and 270. Okay, for part B, I want to make sure that I list these answers in radians, and we've already done 270, so I'm going to cheat a little bit and just say, well, 3 pi over 2 is the solution there because we did that up above. But how do I get the answer in radians here? This is one I really just want you to know the common equivalent for. 30 degrees is definitely pi over 6. Right? 180 divided by 6 is 30, so that makes sense to me. Pi over 6 is 30. Well, 150 is 5 times 30. So you can then just say that this is 5 pi over 6. Another quick way to get that, by the way, is if halfway around is pi, which is 6 pi over 6 in radians, this is just pi over 6 before I get there. So this angle here has to be 5 pi over 6, such that when I add another pi over 6 to it, I get halfway around. So a couple different ways to get these answers, but I do want you to be able to come up with each of these pretty easily, even if you have to start in degrees and then do some converting to radians, okay? All right, that's what we've got for another example. Let's keep going with the process here. Let's try something like, for number 3, cotangent squared theta plus 4 cotangent theta plus 3 equals 0. Okay. So in solving quadratic equations with trig, it doesn't have to be always sines and cosines. It could involve tan or actually the reciprocal of tan. How about cotangent? And if we think about the technique that we're going to use here, this one I actually think is even a little bit easier to factor because we're going to use that add multiply method, right? The things that multiply to cotangent squared are cotangent theta and cotangent theta. And then what multiplies to 3 but adds to 4? Well, it's going to have to be a plus 3 and a plus 1. So that is the correct factorization for cotangent squared plus 4 cotangent plus 3. If you need to use dummy variables to make some sense of it at the start, please go ahead and do that. On this side, you get cotangent theta plus 3 equals 0. And by the way, I realize I've switched over to theta here without really saying much about the fact that we're not using x's anymore. It's the same deal, right? Theta and x, we're treating it the same way. Okay, we're going to solve for theta over the same exact intervals. All right, what do we get on this side? Cotangent theta would definitely equal -3. And on this side, cotangent theta equals -1. Okay. What I'm going to recommend to you is as soon as you solve for cotangent on both of these sides, if you're working with one of the reciprocal functions, change it over to its reciprocal, which in this case is tan. If cotangent equals -3, what does tan equal? Well, it's really -3 over 1 there, so this becomes -1/3, the reciprocal. And what's the reciprocal of -1? Still -1. Okay. So now we're at the point where we can determine the triangles and appropriate quadrants here. Okay. So tangent is negative, all-star trig class. Where is tan negative? Tan's negative in 2 and 4. So we need a triangle in 2 and a triangle in 4. Okay, tan is opposite over adjacent, opposite over adjacent. I want the reference angle x. It's a little tough because it looks like it should be a special triangle, right? If this was a radical 3, I'd actually be in business. But there is no special reference angle when the ratio for tan is 1/3. So how am I going to get the reference angle? To get the reference angle, we're going to type in tan inverse of never -1/3, +1/3. Okay, let's see what that comes out to be. And I'm going to do this in degrees. So if I make sure my mode is in degrees, yes, it is. Okay, tan inverse of 1/3 is 18.4 degrees. And I said round to the nearest tenth if needed. So we've got 18.4 degrees there. That's actually not one of the answers, though. We know the answers are in quadrants 2 and 4. So in quadrant 2, it's 180 minus that reference. And in quadrant 4, it's 360 minus the reference angle. So let's see what those actual answers become. 180 minus the reference is 161.6. 360 minus that same exact reference angle is 341.6. So 161.6 degrees and 341.6. Okay. So that's 2 of my solutions. Let's go over to the other side. Tan theta equals -1. Okay, same deal, by the way. Tan is still negative. It hasn't changed from this problem. Tan's still negative in quadrants 2 and 4. So you're going to draw triangles for me over there. Here's what's weird about tan equals -1. If I had sine equals -1 or cosine equals -1, it's unit, circle, or the graphs. But when tan equals -1, it's going to be triangles. Label it and see why. So tan is opposite over adjacent. This is the same thing as 1/1, right? Opposite over adjacent. and I'm looking for this angle right here. This is actually a special triangle. We don't need the calculator to get the reference angle, although the calculator is pretty smart. So this becomes radical 2, 1 radical 2. So to get the reference angle is just 45 degrees in that special triangle. But like I said, the calculator is pretty smart. If I do tan inverse of not -1, but +1, it does tell me 45. So that's the good news, is if we forget that this is a special triangle, calculator knows it is. So what's the quadrant 2 answer then? 180 minus 45, which is 135. The quadrant 4 answer, 360 minus 45, is 315 degrees. So on this side, you get some really nice looking answers. This side, not so much. Okay, but it's okay. We did have the directions that said round to the nearest tenth when needed. For this one, I'm only going to do degrees. We'll skip the radians one for this one, even though I want you to be familiar with both. I'm okay on this one, leaving our answers as 135 is the smallest. I do like kind of listing them in order from least to greatest. 161.6 would be next, 315, and then 341.6. Okay. So we'll skip the radians for maybe just for this example. And let's see if we can do one more together, one more quadratic to solve. All right, last one for today is solving 5 cos squared x minus 3 cosine x minus 7 equals 0. Okay. So we got a lot of prime numbers there, 3, 5, 7. If I were to try the factorization here with values like 5 and 7 as the start term and the last coefficient here, you're never going to get that to come out to be -3 cos x in the middle. No matter what pairing you choose for your factors, it's just not going to happen. So here's the good news. When we have a quadratic, if we find that we have a situation where it's not factorable, we know we can still use quadratic formula. Oh boy, do I even have to sing it to you? I think I can sing it. We'll see if I can try. All right, quadratic formula usually goes x equals -b plus or minus the square root, but guess what it's going to be now? Cosine x equals -b plus or minus the square root of b squared minus 4ac all over 2a. All right, so just be a little bit careful here that it's really not x equals anymore. It's the function cosine x equals. And what are my values for a, b, and c? A is 5, b is -3, and c is -7. Okay, let's plug those in and see what happens. Cosine of x would equal -b, which is 3, plus or minus the square root of -3 squared minus 4 times 5 times -7 all over 2 times 5. Can't help but sing it, sorry. All right, cosine x equals 3 plus or minus. Let's talk about what this number is under the radical. I would just type that in the calculator to make sure we avoid any computational mistakes there. -3 squared minus 4 times 5 times -7. The number under the radical is 149, which is not standing out to me as a perfect square. Okay, and then that would be all over 10. All right, here's what we do now. You've got to split this. We're going to split it up at the plus or minus, okay? So on one side, cosine of x would equal 3 plus radical 149. Actually, I'm going to do a fancy fraction just to make sure we're good. 3 plus the square root of 149. And then I'm dividing that by 10. Cosine x equals 1.5206 ... Okay. Well, guess what? This is not a special triangle. No surprises there. Cosine's positive in quadrants 1 and 4. How am I going to get the reference angle? By doing cos inverse of 1.5206. Okay. Now, maybe some of you are getting a little nervous about this, but look what happens. Cos inverse of 1.5206 is an error domain. What? Why is that the case? Well, think about the good old cosine curve. Cosine goes from -1 to 1. So if you ever have cosine of x equals something outside of -1 to 1, we know that there is no solution to this part of the equation. That's kind of crazy. But we're going to see that start to come up in these questions where maybe we have quadratics we solve. Cosine x can never equal 1.5. So therefore, cos inverse, it made sense that there was going to be an issue there. Let's talk about what cosine x could equal, though, if it was 3 minus radical 149 over 10. Let's try that. So fancy fraction, 3 minus the square root of 149 divided by 10 is negative 0.9206. Is that okay for cosine? Is that within the range from negative 1 to 1? Yeah, it just squeezes in there, but negative 9.92 is probably going to have 2 solutions right there. And they're going to be in the quadrants where cosine is negative. So it's going to be a quadrant 2 and a quadrant 3 answer. All right, you ready for this? To get the reference angle, what am I going to type in? Cos inverse of positive 0.9206. Okay, don't do the negative. All right, I already have negative on the calculator. How can I make it positive? I'm going to multiply it by negative 1. Now it's a positive. Then let's do cos inverse of that. Cos inverse of that is a reference of 22.97. Let's just round that nicely to 23.0 degrees. That's the reference angle. I need to put it in quadrant 2 and in quadrant 3. In quadrant 2, it's 180 minus the reference. And in quadrant 3, it's 180 plus. Okay. Last steps here, do 180 minus this reference angle. And then do 180 plus. Go ahead, get that reference again. The 2 answers are 157.0 and 203.0. So 157 and 203.0 degrees. Those are the 2 solutions, and the only 2 solutions, because on this side, we've got that little no solution case that came up. Okay. This is as tough as it gets, and I understand there was a lot going on here. I just kind of threw quadratic formula at you. I'm like, yeah, let's go right for it. I hope you were able to follow the process, but I can promise you that we will do a lot more like that. So if this was a little bit tough for you, there's a lot of calculator steps to consider. There's more to come with quad formula in the future. So if you have any questions, let me know next time we're in class. Otherwise, have a great rest of your day.